Good morning, everyone. The topic of my research is variable delay, low pass, all pass filters and their applications. The overview of the presentation includes introduction to variable delay filters and their applications. Then we will have a quick summary of the reported variable delay filters. Then we'll come to the thesis contribution, highlighting each of the contribution, and we'll discuss. The first thing will be variable delay low pass filter using Miller effect. The next contribution of the thesis is a variable delay GMC all pass filter with tuned GM. Next one will be the study of TTD non-idealities in timed array receiver. Finally, the presentation will be concluded with conclusion and future work. Continuous time all pass filter offers certain amount of delay to an input signal. The delay of the all pass filter can be varied by changing the value of L and C. In case of GMC implementation, the delay of a filter can be varied by using a variable order or a variable bandwidth technique. Further, in variable bandwidth technique, the delay of a all pass filter can be varied using a tune C or a tunable GM approach. Low pass filter with a certain amount of bandwidth also offers certain amount of delay to an input signal. The delay of a low pass filter can be varied by changing the value of RC. So coming to the application of a variable delay filter, they find its application in expansion of narrow sporadic pulses. Modern data acquisition systems such as ground penetrating radars, through wall imaging systems, or even the indoor localization system identify the position of the object by transmitting narrow continuous time pulses. The reflected signal is then analyzed in order to understand the position of the object. The reflected pulse in these applications are narrow, sporadic, continuous in nature. Digitizing these narrow pulses require high-speed analog to digital converter. The requirement or the disadvantage of using high-speed ADC can be avoided by expanding these narrow pulses in time without affecting the shape. The expanded pulses will be then digitized using low-speed analog to digital converter. The next application of a variable delay filters find in implementation of TTD circuits for baseband wideband beamforming techniques. So basically, in the beamforming, the signals are delayed and added constructively in order to improve the signal strength. The variable delay all pass filter find its application in equalizer, and variable delay low pass filters are used in the realization of voltage controlled oscillators. Now we will have a literature survey on variable delay filters. Transmission line also, which acts as a all pass filter, acts as a delay element. The delay of a transmission line can be varied by changing the value of L and C, or also using a length of a transmission line. In case of a tuned LC approach, the value of L and C are varied for different delay settings. In case of trombone topology, the connection between the input and the output transmission line are programmed using a path select amplifier in order to change the length, and hence the delay of a transmission line is varied. In case of a switch line approach, the input is passed through a programmable delay lines using SPDT or DPDT switches. These delay blocks can be an identical all pass filter, or it can be a different all pass filters of a different order. So these variable delay filters are used in the application of programmable delay lines for beamforming applications. But the problem is because of the limited quality factor of inductor and capacitor and other switching losses, the realized TTD suffer a certain amount of losses. The next approach of delay tuning is a variable order constant bandwidth filter. So basically here the delay tuning of the filter is done by changing the order of the filter, say from order 9 to 2. So in order, as the order of the filter and the bandwidth of the filter is kept constant for changing the every order, so the capacitance is also varied in order to keep the bandwidth constant. So this particular application is used in the realization of wideband TTD circuits. But the problem with this type of approach that it has to design a very large higher order filter and it consumes a larger area and also consumes more power. So the next delay tuning technique is a variable bandwidth filter technique with the tunable GM. So this is a second order all pass filter in which the delay of a filter is varied using a varactor CS. And in case of first order all pass filter, the delay is varied using a tuned C using a switched capacitor architecture. So this variable C active GMC filter are used in the realization of programmable delay line. However, with the low quality factors and the all pass filters also require additional buffer stage. The first order GMC active all pass filter with switch C would also require an additional gain enhancement technique. The next technique is a variable bandwidth filter in which with using a tune GM. The application of this particular circuit is in the expansion of narrow pulses. So basically the main principle is any continuous time signal whose width has to be stretched, the time constant of the filter is varied by using an external signal alpha. So once the signal is completely inside the filter, the bandwidth of the filter is varied by reducing the alpha from 1 to 0.5, which reduces the bandwidth and increases the delay. So as I previously mentioned, this is a tune GM approach. The reduction in the bandwidth is done by changing the value of the GM. So so this is basically changing the delay of the filter using a constancy approach. The main problem is it requires to implement a higher order filter, and the GMs has to be switched instantaneously and precisely for the pulse expansion. The variable delay filters, the delay of a low pass filter can be varied using the changing the value of the capacitors, or it can be changed by changing the value of resistance, which can be implemented using a voltage controlled PMOS devices. So the realization of from this variable delay low pass filter in the realization of voltage controlled oscillators, but it requires, the problem with this particular tuning approach is that it requires high quality capacitors, and the frequency of oscillations must remain will not remain constant throughout the frequency range of the VCU. Next we'll come to the thesis contribution. The first contribution is, right now we have seen most of all the TTDs are realized with an all pass filter. For the first time we have explored how a low pass filter can be used in the realization of a TTD circuit using a Miller effect. The further same principle will be extended to other applications such as pulse expansion, compression and ring VCO circuits. The next contribution is the realization of a TTD using a lower order GMC all pass filter. The principle will be further expanded to a pulse expansion and compression techniques. We have also proposed a new inline correction technique for the impedance cancellation in high gain OTA. And the last contribution of the thesis will be focusing on study of TTD non-idealities on time delay receiver. So let us now understand and go through each of the contribution one by one. The first contribution is a variable delay LPF using a Miller effect. So this is the first order proposed RC circuit in which the delay of the circuit is varied with an external control alpha. So in order to understand intuitively, for example, when alpha is equal to 1, the current is 0, and for alpha is equal to minus 1, the current will be different. So in this way, as basically the impedance observed from the Vin will be different depending on the different values of alpha. So in this way, by changing the value of the alpha, the equivalent impedance observed from Vin is going to vary, and hence the delay of the filter is going to vary. So if we observe mathematically the transfer function of the system, for alpha is equal to 1, the circuit behave as an all pass filter, and for different alpha with certain range, it behaves as a low pass filter. Figure shows the gain and the phase plot for the different values of alpha. So in this way, by changing the value of the alpha, the circuit behavior varies, and within the region of the constant gain and the linear phases, the circuit can be used in the realization of TTD, expansion, compression, or in the VCO applications. So let us see the implementation of a TTD circuit using a variable delay low pass filter. The proposed low pass filter offers certain amount of delay, and the low frequency group delay is 1 minus alpha times of RC. So within the region of the constant gain and a linear delay, that is a fixed delay, the low pass filter can be used as a TTD element. But the delay range obtained from a single LPF is very small. So in order to improve the delay range, we have cascaded n stages of similar stages in order to have an improved delay range. So this is the differential architecture of the low pass filter used in the TTD implementation and the circuit level implementation using the transconductors and resistors and capacitors. In the case of end stage implementation of a TTD, the first stage or there exists a because of the on-chip implementation, there exists a parasitic capacitance from its own stage and from the succeeding stages. So when we analyze this carefully and accounting for the parasitic capacitances, the equivalent circuit can be written like this, where CP1 and CP2 corresponds to the parasitic capacitance. If CP1 is equal to X times of C and CP2 is equal to Y times of C, it can be seen that from the transfer function, the circuit no longer remains a first order, it's a second order system, and the group delay, the low frequency group delay of the low pass filter depends upon the value of the parasitic capacitances, and this will be the new range of alpha in the presence of parasitic capacitances. And why this is important, let us have in more detail. So this is the value, this is the delay gain and the delay plots of the low pass filter in the presence of the parasitic capacitances. The actual implementation shows that CP1 is almost 2 times of C and CP2 is equal to 0.5 times of C. So when we compare this particular response with the ideal nature, so one can see that though in the presence of the parasitic capacitances, the delay range of the TTD has been improved, but it has affected the 3 dB bandwidth of the filter. So, and why this becomes important, because for a design point of view, it also depends upon the number of stages which has to be cascaded in order to design a TTD for a given delay range bandwidth factor. Considering these things, so we have designed and implemented a 10-stage TTD circuit in UMC 180 nanometer technology, and the post layout simulation result shows that TTD shows a delay range of 450 picosecond with a delay variation of plus or minus 60 picoseconds and has a gain deviation of plus or minus 4 dB. Now, as we previously seen that the LPF has a low frequency group delay of 1 minus alpha times of RC. In practically, the delay remains constant up to certain amount of frequency and then decreases. So in order to have a constant gain up to certain frequency, say omega B, we need some sort of a delay correction where the delay increases with the frequency in the region from omega A to omega B, such that the overall delay of the filter remains constant up to omega B. So we need some sort of a delay correction technique which maintains a constant delay up to the desired frequency omega B. So how to generate a delay which increases with the frequency in the region from omega A to omega B is the question. So the answer is we use the similar first order circuit, whatever the previous circuit with the Miller effect, but with a different set of control signal beta, where the beta ranges from 1.2 to 2. So in this case, one can see that the delay increases from omega A to omega B within this region. And why this is happening? So that can be understood from the phase response as well as from the pole 0 plot. So as the left hand side 0 occurs before the pole, there has been an increase in the phase, and that's why we see this increase in the delay response. So using this, we have come up with the TTD with the delay correction technique, where the low pass filter is cascaded with delay correction. The value of beta required for the delay correction is detected by inspection method. So graph shows for alpha is equal to minus 2, the inspected value of beta is equal to 1.6, and it maintains a constant delay up to frequency of omega B. One can see that with this the constant the bandwidth has been improved by a factor of 2.5, up to which the delay remains constant, but at the cost of increase in the power by a factor of 2. So using this delay correction method, so we have designed a 15-stage TTD which includes a delay correction. and the post layout simulation result shows that the delay range of a TTD is around 400 picosecond with a very minimal delay variation of plus or minus 5 picoseconds. The proposed TTD architecture was compared with the existing reported architecture, which is implemented with the passive as well as active based all pass filter. Accounting for the figure of merit 1, which accounts for the power dissipation, delay range and bandwidth, the proposed TTD with the delay correction has a figure of merit of minus 20.92. But it is observed that it is seen that the TTD should also account, this figure of merit should also account for the delay variation as well as the gain variation. And why it is important, we will also see in the future slides, that accounting for the figure of merit 2, which accounts for the delay variation as well as the gain variation, out of all the active based TTD architecture, the proposed TTD shows a minimum figure of merit. Though the least reported has a minus 57.69, though it has a lower figure of merit, but it has a larger gain deviation. Next, we go for the next application of the variable delay low pass filter, that is in the pulse expansion and compression technique. The same principle is used here. So within the region of a constant gain and where the delay will be linear in nature, the continuous time pulses can be expanded or compressed depending upon the value of alpha. So any continuous time pulse whose frequency fall within the region of constant gain and a linear delay can undergo an expansion when alpha, if it is decreased linearly, so which basically forces the delay to increase linearly, and that would lead in expansion. Similarly, any wider pulse which comes to the input of the circuit, and if the alpha is increased linearly, the group delay would reduce linearly, and that would lead in the compression. So in this way, the same circuit can be used in the application of expansion as well as compression for the different profile of alphas. The expansion or a compression factor from a single stage LPF will be very minimal. So in order to have a better expansion factor, we have an end stage signals need to be, stages of LPF needs to be cascaded. As I previously mentioned that the control signal must be linear in nature. So in order to have the alpha which increases linearly or decreases linearly, it's basically a ramp signal. So an external sinusoidal signal is first converted to a differential square wave, and the differential square wave is then applied to the on-chip ramp generator to generate a differential ramp signal, and the succeeding stages of the expansion or the compression blocks control signal is also delayed by certain amount of time. So next, using this, so we have we have generated designed and implemented a 15-stage expansion circuit designed in both UMC 180 as well as TSM 65 nanometer technology. Coming to the post layout simulation result, in order to validate the expansion process, on-chip Gaussian pulse of half power pulse width of 350 picosecond was applied as a test input, and the result shows that the signal was stretched with a stretch factor of 2.25 with the with the error of 1.5 millivolts within the region of half power pulse width. Similarly, with the same principle, we have designed a 15-stage compression, and in order to validate this, an ideal Gaussian pulse of 3.32 nanosecond was applied as a test input, and we obtained a compression factor of 0.47, and the error between the actual and the ideal compressed pulse was around 1.05 millivolts within the region of half power pulse width. The proposed expansion technique is compared with other reported architecture. So unlike the photonic based expansion, which required a lengthy optical cables for the expansion, this technique do not require those things. And also the dispersive filter and photonic based a highly linear chirp carrier, which where this particular technique do not need any such highly linear chirp carrier signal. Though the sampling based expansion shows the better stretch factor, but it includes a very power hungry clock network for the expansion technique, which is again not required in this architecture. So overall, this is a very simple architecture, and it also does not require are designing of a higher order variable bandwidth filter for the expansion process, and we are able to get a good stretch factor of 2.25 with a very minimal power consumption of 36 milliwatts. So the next, we go to the next application of a variable delay filter, that is in the implementation of three-stage ring VCO. The delay element what we have used is CML buffer type, in which the value of the capacitance is varied using an extra signal alpha, which is a Miller effect. The principle is same which is discussed before. Here the value of C is varied with an external control signal alpha, and hence the frequency of oscillation is going to vary with this alpha. And this particular delay cell, the tuning technique do not require a high quality varactors, and also it maintains a constant frequency of oscillation across the entire frequency tuning range of the VCO. So the first one, the three-stage VCO, was designed and implemented in TSMC 180 nanometer technology. So by varying the control voltage from -100 millivolts to +100 millivolts, the frequency tuning range was from 3.6 gigahertz to 4.8 gigahertz, and the phase noise was from -86.5 to -90 dB. The similar architecture was implemented in TSM 65, and the frequency tuning range was from 4.7 gigahertz to around 8.4 gigahertz, and the worst phase noise is around -76.76. The proposed VCO architectures were compared with a report CML based delay cell. So considering the figure of merit, which is higher the better, which accounts for the power dissipation, offset, the phase noise, as well as the frequency tuning range, the proposed VCO shows a better figure of merit compared to other CML delay based VCO architectures. Next, we come to the second contribution of the thesis, which is basically variable delay GMC all pass filter with tune GM and their applications. This figure shows the third order Bessel all pass filter, in which and this, for example, for a given set of C1, L2 and C3, if tau G1 represents the group delay of the all pass filter for a given bandwidth F1, reducing the values of the inductance and capacitances would reduce the delay from tau G1 to tau G2 by increasing the bandwidth. Similarly, as the value of the inductance and capacitors are reduced, the group delay would reduce and would increase the bandwidth. So within the region of the constant delay, the all pass filter can be used as a delay element. So the basic thing is so we have designed this with a lower order filter. So when it comes to the GMC architecture, the value of the delay is varied by changing the GM. For a GMC implementation of the all pass filter, the low frequency group delay can be varied by changing the GM. That GM can be changed by changing the value of the bias current I0. The main advantage is that the delay tuning is done using a lower order all pass filter, and it do not require a high quality varactors for changing the delay, and the delay of the filter is varied by tuning the GM, and the application of this APF would be in the TTD and pulse expansion and compression technique. So now we will see how the TTD element is realized with this architecture. So within the region of the fixed delays, the low pass filter can act as a TTD element. In order to improve the delay range, 3 stages of third order variable delay all pass filters have been cascaded, and the anti-aliasing filter preceding this TTD band limit the signal such that the delay range will be that the frequencies fall within the range of F1. So now coming to the implementation of the variable GM in the third order all pass filter. So as I mentioned that here the delay is varied by changing the value of the GM, and how the GM can be varied by changing the bias current I0. Here the current tuning is done with the constant GM bias circuit, where The bias voltage is varied using a constant GM network with different values of resistances, such that the GM has a linear relationship with R, and by tuning the value of R's, the GM of the circuit are varied, and hence we get a programmable delay with this particular architecture. The proposed TTD was implemented in 65 nanometer technology with a supply voltage of 1.2 volts, and the delay ranged from 1 nanoseconds to 1.8 nanosecond with the gain deviation of plus or minus 0.16 dB. So the proposed all-pass filter based architecture was compared with other reported GMC architecture. The proposed TTD has a minimum gain variation of plus or minus 0.16. But it has a not that good FOM2, which is compared to the low pass filter based architecture. Next we go to the next application of the APF, that is in the pulse expansion and compression. Again, the same principle within the region. As the group delay is varied linearly, the circuit can be used in the expansion as well as in the compression. In order to improve the expansion and the compression factor, identical 3 stages of APFs are connected in cascade. Then coming to the tuning of the GM, which is the basic principle here, the programmable GM for this expansion and compression is achieved using a Gilbert multiplier as a programmable delay element. So one can see that as the value of alpha is vary, the equivalent GM is going to vary, and in order to have a better gain of the GM, so there is a negative impedance cancellation technique is also attached in this, is also shown here. So this is how the programmable GM are realized for a Gilbert multiplier for expansion as well as the compression. So decreasing the value of alpha in time would lead in expansion, increasing the alpha in time would lead in the compression of the pulses. The architecture was implemented in TSM 65 nanometer technology. Simulation result shows that with the ideal Gaussian pulse of 0.944 nanosecond, we can there is a stretch factor of 1.48. And for the same input of 0.944 nanosecond, there is a compression factor of 0.85, and the error between the ideal and the expanded pulses are within plus or minus 1 millivolt for the expansion as well as for the compression cases. In order to have a quantitative analysis between this expansion stages, which is done with the APF and LPF, so we have taken a scenario where an input pulse of 0.44 nanosecond was applied, as was given as a test input for the expansion, which is realized with the all pass filter as a low pass filter, and we obtain the same stretch factor of 1.04, where the all pass expansion circuit was designed with a one stage variable delay all pass filter, and the expansion circuit was designed with a 3 stage variable delay low pass filter. For the same stretch factor, for the same pulse width, so it is observed that the low pass filter shows higher error compared to the all pass filter, but it shows a lower power dissipation. So the important observation to be is that there is a trade-off between power and accuracy. So in order to have a better stretch factor, so we go for an all pass filter which consumes a higher power compared to the low pass filter based architecture. Next is the inline calibration for high gain OTA. The GM block in GMC all pass filter, the transconductance forms a critical component. The gain of the DC gain of this particular OTA should be very high. There are different ways to increase the gain, and cancelling the impedance using a negative impedance is one of the technique. So in order to do that, normally we need an external replica circuit to cancel the impedance, but if there is any mismatch in the replica circuit, so that would deviate the gain of the ATA. So what we have done is we have proposed a new correction technique where without any replica circuit, the gain of the OTA can be improved for this where the negative conductance is tuned in case of high gain OTA. The main principle is configure this OTA in a negative feedback, and once the OTA is configured in a negative feedback, we obtain a steady state error VE. So forcing this steady state error to 0 by another negative feedback, the gain of the OTA can be improved. Let us see how. So the effective output conductance here G0 N is basically G0 minus Gn, and the DC gain of the OTA is Gm by G0 N. There is another negative feedback which works in tandem and which forces this steady state error to 0. So once this steady state error to 0, my G0 becomes Gn, and hence the output conductance becomes 0, and the gain of the OTA will be high. So this particular technique was implemented and designed in a TSM 65 nanometer technology. So the simulation result shows that with the proposed inline correction technique, the OTA gain was improved from 18 dB to 55 dB, and across all the process and temperature, a minimum gain of 50 dB is maintained across all the corners with this inline correction technique. Next, we come to the third contribution of the thesis, that is the study of TTD non-idealities in timed array receiver. In case of consider an example of baseband beamforming, the down converted signal will be delayed and added constructively in order to achieve a beamforming. The delay can be done either using a variable phase shifters or TTD. But the problem is, as the bandwidth of the baseband signal increases, the phase shifter do offer beam squint, and this would affect the performance of the system. So generally for a wideband signals, true time delay elements are preferred over phase shifter for the beamforming, and the ideal TTD circuits must maintain a flat delay and constant gain in order to have a proper beamforming process. But we have done a literature survey on different TTD circuits, and the practical TTD circuit do show certain amount of delay variation as well as gain variation. So if we see particularly in case of LCD based TTD, so there is a gain deviation of plus or minus 4.4 dB and a delay variation of 14%. Though some of the architecture in a trombone topology offers a lower delay variation and gain variation, it has a minimum delay range, that is a maximum delay up to 11.57 picoseconds. Coming to the summary of the APF based TTD, the gain variation is around plus or minus 15 dB and the delay variation is around 24%. And some of the architecture, though there is a minimum delay variation and the gain variation, the delay range and the maximum delay is only 50 picosecond. So this forms an objective for us that though it is said that TTD are the ideal candidate in case of wideband beamforming, practical TTD do offer certain amount of delay variation and gain variation, and none of the reported literature survey do not address this problem, how this delay variation and gain variation would affect the system level performance at the system level using this non-ideal TTDs. So taking that as an objective, so we have analyzed how the practical TTD would affect the timed array receiver. So the case study is done for the RF beamforming as well as the baseband beamforming. For this we have considered a 4x1 timed array receiver, and the example is a 5G millimeter wave receiver with the carrier frequency of 28 GHz and bandwidth of 1 GHz. With an ideal TTDs, it is observed that the radiation pattern should not have any gain variation and there should be no beam squint. But considering different delay variation and gain variation from the TTDs, it is observed that from the radiation pattern of this 4x1 receiver do shows the gain deviation and there exists some amount of beam squint. The next case is a baseband beamforming architecture, and we have considered the same case of 5G millimeter wave receiver with FC is equal to 28 GHz and bandwidth of 1 GHz. And with ideal TTDs, it is expected that there should be no beam squint, but with different delay variation and gain variation and its combined effect. So we do see certain amount of beam squint with this particular with this non-ideal TTDs. So it can be observed that even the TTD offers certain amount of beam squint at the over system level architecture, though compared to the phase shifter, they they offer less amount of beam squint, but the practical TDD circuit also offers certain beam squint, and it is very important for a design point of view to consider these gain variation and delay variations for designing these TTD circuits. So coming to the conclusion, we have come up with a novel delay tuning architecture where the impedance of the circuit is varied the first of a low pass filter using a Miller effect, and this delay tuning technique was used in the realization of a TTD circuit. So basically alpha with different time profiles to a low pass filter is used for a desired application. So if alpha is a fixed DC and with certain range, the variability low pass filter will be used in realization of TTD and VCO applications. If the alpha is linearly decreasing, it can be used in an expansion operation, and if the alpha is increasing linearly, it would lead in a compression. The next contribution is that we have come up with a cascadable lower order all pass filter to realize a TTD element, and the delay tuning is achieved using a programmable GM without using any high quality varactors. And the different delay tunings are achieved with the different by changing the GM. In case of a TTD, the GM is varied by using a constant GM bias by changing the value of R. For expansion technique, the Gilbert multiplier acts as a programmable GM for expansion and compression. And we have also proposed an inline correction technique for an impedance cancellation in a high gain OTA, where the impedance cancellation is done without using any replica circuit. Next, we have done a quantitative comparison between LPF and all pass filter expansion technique, and what type of expansion circuit to be used depending upon the applications. Next one, the effect of TTD non-idealities on beamforming circuits. So particularly on RF and baseband beamforming is analyzed. So next, coming to the future work, will be the respin of the tape out of the TTD and expansion designs which have been fabricated in 65 nanometer technology. Then using the proposed TTD, we can develop a certain complete receiver block for the beamforming architecture, maybe for example 1x8 receiver with the proposed LPF based TTD circuits. And as we told that inline calibration would increase the gain of the OTA block, and that GM block can be used in the complete GMC all pass filter based designs. Next future work would be the optimization of LPF and APF design, considering distortion and noise which was not taken into account for the current design. So considering those distortion and noise, the design need to be optimized. Now, and also here the delay tuning was applied with the Miller effect was for the R and C load. So the delay tuning can be further expanded to any load of any complex filter for the tuning of the delay using a Miller effect. And we can also come up with a variable order filter. Here the order of the filter is fixed, so we can have a variable order filter with the Miller effect to the further increase the delay range. And we can have a tunable band pass filter realized with the variable delay filters which are used in GNS and GPS receivers. The proposed delay techniques can be used in the application of an equalizer, which can be another area where this delay tuning techniques can be used. These are the patent and publications from this research work. Thank you.